when this psi goes to 0, we assume that the material is completely destroyed. So based on these considerations, there can be introduced a kind of a damage metric that is defined exactly by this 1 minus psi from intact material to the fully damaged material. So this theory has been used later on by Lemaitre to introduce also the elastic properties of the materials in the equations. And in this case, we have the stiffness of the undamaged material, E0, and the stiffness of the damaged material. And actually, if you see this last equation here, it's like the same equation that we had before, but the psi, this function for this variable for defining damage, is now replaced by the ratio of the stiffness of the damaged material over the stiffness of the undamaged material. And this is what is used or has been used by many researchers. Of course, again, changing this relationship to fit better the experimental data by having not a linear relationship that we see here, but it might be that there is a relationship that is exponential in both sides of the linearity. I will explain what I mean by that. So later on in the 1980s, and coming now to composites, we had the description, the clear description of the stiffness reduction curve, so the evaluation of stiffness with time. And it was mainly the group of Karl Schulte that distinguished these three stages. The first stage, you remember, we had the stage that stiffness is dropping quite rapidly. And this was attributed mainly to matrix cracking in the material system. Then we have the intermediate region, where we have an approximately linear degradation of stiffness with the loading cycles. And then we have the final stage 3 in the diagram, that is attributed to the final failure of the material. The benefit of stiffness, and this is why it is appreciated, if you like, from engineers, is that you can measure it during loading. It's also a measure that can give an assessment for the material performance without having to do any destructive testing. So it's a non-destructive method to follow the progress of the material capacity, and as such, it can be used also as a performance criterion for the material. You can imagine structures that are having rotating parts. Imagine a wind turbine rotor blade that rotates, and due to the damage, the stiffness is reduced, so the blade becomes more flexible. And at a certain point, the stiffness reduces so much that the blade hits the tower. So this is, of course, not acceptable. So there, instead of talking about failure criteria that are related and are constrained only to strength values, so that the material does not fail, we might also assign performance criteria, in this case, criteria based on stiffness, that can say, for example, that the stiffness, if it is more than 10%, if it drops more than 10%, then we assume that it is the material it is failed. So these residual stiffness models that we've seen are mainly deterministic, but can also be assigned to statistical considerations. So models have been introduced in the past. As we said, they are based on a critical value, like the stiffness degradation. And there are a lot. I will not go into details. You can easily find all the models that exist. Later on in the prediction part of this presentation, we'll see also simple models and how they can be used in this predictive case. So to summarize, stiffness degradation is a very nice measure that can be used during fatigue life non-destructively to assess the material performance. The residual stiffness is calculated by measuring also the strains together with the load and the number of cycles. The simple model or the simple concept behind this is that we have reduction of stiffness, and this is measured by the ratio between the initial stiffness and the stiffness at a certain time over the initial stiffness. And we define damage in this sense from 0 to 1. So it's a scalar variable that defines if we are close to failure or not. Later on, we'll see. I'll just introduce it here. We discussed about this also 2 days ago, that damage can be linear from 0 to 1. If this is life, number of cycles, and this is damage. Damage can be linear. This is exactly what we describe by this equation. But damage can be also delayed in the beginning or accelerated in the beginning. This is non-linear damage. And in composite materials, we've seen that there are a lot of cases where we have non-linear damage and not this linear damage development. And this is discussed in the literature quite widely. And that's why you will see also in the literature models that are not assigning the damage to a linear relationship between these two, but there are equations that have here polynomial or exponential relationships between the two stiffness values that are used. So the stiffness degradation theories in reality are applied in a lot of, independent of the material. They're based on the measurement of stiffness that can be measured by measuring the slope of the cycle, the hysteresis loop area. So the slope drops, and this defines the slope, the stiffness drop. And also the interior is the damage. As we said, here we can, as we've seen in the previous lecture from Professor Bedi, we can also estimate the creep. But if we only stick on the damage, so the stiffness drop, we can plot. These are values. You see also the scatter of these measurements. These are values from 6 independent specimens at different stress levels. Again, here you remember the discussion that we had, that the stiffness drops more when the stress is lower. So that's why we see these black dots, for example.
So among the colleges who are not able to deactivate earlier, are some of them able to deactivate now?
And it is less for higher stress levels. And this is a trend that is more or less followed by all the specimens and all the materials that we have investigated. So I'm showing measurements, and in this case, I come back to the measurements that we have seen yesterday for the adhesive material. And there is exactly the effect of the conditioning of the material, or the conditions of the testing or of the operation of the structure. But in some cases, as we've seen also yesterday, we might have stiffness that is increasing instead of decreasing. And this can be due to the plasticization in this case, due to additional curing of the material with time in other cases, due to the alignment of fibers in the system that we've seen for plus minus 45 degrees. And this is actually a validation of the argument that we had in the beginning of these lectures, that composites follow specific trends. Like for stiffness degradation, we expect to have this sigmoid drop of the stiffness, but there are cases where we should be more careful when we assign values to stiffness degradation, because there are specific peculiarities of the materials that suggest that the behavior might be different than this. So based on stiffness, as you remember before, we mentioned that we can define design allowables, if you like, that do not correspond to failure, but correspond to specific stiffness degradation. And this is how we defined once these stiffness-based SN curves. They have been introduced initially by Salking 30, 40 years ago, but we also developed a model in our group here, assuming or assigning the failure data. So here you have the stress amplitude, you have a number of cycles, and then you see here is exactly the stiffness degradation, then the stiffness at number of cycles n over the initial stiffness of the first cycle. And by doing this, you can estimate model parameters, and you can design and you can show at the end an SN curve that is, I will just open it here and discuss it. So SN curves that correspond to specific stiffness degradation and not to failure. So what we see in this diagram, we have the experimental data. This is again the material number one, the first one that we extensively discussed yesterday. And this is the material at 15 degrees of axis, R equal to 0.1. The SN curves, the 50% reliability SN curves and 95 reliability SN curves for the material are plotted with this dashed dot line. So this line and this line. And here you see the stiffness-based SN curves for 87% stiffness degradation or 96%. Sorry, 87% remaining stiffness. So this is 13% stiffness degradation or only 96% remaining stiffness, which means only 4% stiffness degradation. So the idea here is that we accept, if I try to read this diagram again in a different way, I accept my material to be in operation only until it loses 4% of the stiffness, which means that I'm very conservative in this case. I'm very secure. And this is, to my understanding here, is correlated to the 95% reliability level curve. And these values here, I selected these values not randomly, not without any prior analysis, but I was based on the model that I did on the stiffness degradation data, that if you remember, we said that they follow a Weibull distribution. But then even if I only use, so I can do this analysis with the Weibull distribution, but I can also use the experimental data directly and plot the distribution of the experimental data and check, for example, what kind of value of stiffness degradation corresponds to 50% for this distribution, and what value of stiffness degradation corresponds to 95% of this distribution. And this is how I defined these levels. So you can see from this graph that you can use these SCN curves, the stiffness degradation SN curves, as design allowables to confirm that your structure, so having now a performance criterion, confirm that your structure will not deform more than a specific limit that you can set. So we've seen also in other cases for other materials at 45 degrees, 90 degrees, that this correspondence is always valid. So we go briefly to residual strength degradation theories. And this residual strength is based, these theories are based on the measurement of the strength of the material after specific numbers of cycles, so during the fatigue life. So you can imagine that this is very intensive experimental program, because you have to start testing a specimen, stop the testing before the specimen fails, and do a static strength test. And then at the same stress level, you have to go back, take another specimen, do the same, and again collect remaining strength points. If you do like that, you have a curve like this that tells you, so this is the degradation of the specimen strength, so the specimen strength, after being loaded at a certain level for a specific number of cycles. And we've seen that this relationship is usually linear. So there is a linear degradation trend that doesn't show for many materials, it does not show any indication of degradation. So it doesn't follow actually this linear degradation in the sense of monotonic degradation. It is linear until a point where we have what we call the sudden death. And this is the reason that this is one of the reasons that these methodologies are not very commonly used, because they do not, specifically for materials that are highly anisotropic, they do not give initial or indications of failure during the lifetime. Another reason that these methods are not very common in practice is that they need a lot of experimental data. So I can explain here how we collect these data points, explain exactly the theory. We have I imagine we have our experimental data, failure in fatigue. We have the static strength data. We have also the residual strength data, which means that in this case, we pick a specimen, we start loading the specimen, but we do not let it fail. And then we stop the test, the fatigue test, and we do residual static strength test. And this is how we collect these points. And if we collect these points, then we have the line giving us an impression about the residual strength of the material. So these models shows, as we said, in all models, there is a monotonously degradation of the strength with lifetime. This is obvious for all of them. On top of these methods that we discussed before, we have the fracture mechanics theories that actually they follow the development of a crack. In metals, there is only one crack that propagates. In composites, if you talk about composite laminates, we have a lot of different cracks that are associated to the energy that is released by the specimen, or it's on the other hand the energy that we impose to the specimen to damage the specimen. So the idea there is to follow the crack propagation and then have specific theoretical models that allow the extrapolation or the interpretation of these experimental results to give some equations like some curves that are similar to the SN curves, but do not correspond to number of cycles and load, but actually they attribute the rate of crack propagation per cycle. So this is the rate of crack propagation as a function of the load. So this G is introduced is the strain energy release rate. So actually the energy that we need to give to the system to propagate the crack for a specific distance as a function of the rate of the crack propagation. And this curve has been introduced years ago. I don't know if I have here. No, probably not. Has been introduced years ago. We discussed. Yes, this was there. I thought that I have here the discussion about the introduction of this fracture mechanics, but we've seen this in the first day. So it's the curve that has been introduced by Paris. That he suggested that this first linear part of the curve can be fitted by a power law equation, and actually in the model it's the Paris equation is what we see here, is this part of the model. Then others, having seen a lot of experimental data as those that we see in this graph, for example, they've seen that this model is not capable of fitting or simulating the entire range of the experimental data. Actually, the model, this Paris law model, corresponds to this, or probably a bit further, this linear part. But then to correlate also this part and this part to the model, they introduced additional terms. This one corresponds to this term, to this part, and this one corresponds to this part. So this is related to the G max, the maximum value of G that we can assume to the specimen, and this is related to the static value of the G that we have to the specimen. And this term corresponds to the threshold. You remember that also in the SM curves, we said that there is a value that below this, more or less, we have very slow damage propagation. So in FCG curves, the fatigue crack growth curves, we also have a threshold that below this, theoretically, we don't have any damage at all. So this threshold here is used by a lot of industrial domains to design structures for safe life. So design that does not accept any damage to occur in the structure. For example, aerospace designs airplanes having this consideration in mind. So they never accept having any damage in their materials. Of course, you can imagine this is a safe approach, but it is also very costly. And that's why in some cases we prefer to have damage. So there we talk about the damage tolerant fatigue designs. So we can accept having damage in the material with the condition that we can control this damage or we can monitor the damage. So if we know that there is damage in the material and there is a crack that propagates with 10 to the -5, it means it needs 100,000 cycles to propagate for a millimeter. And we assume that this is safe for our case. And during the next operation, before the next inspection of the structure, we'll do much less cycles than this. Then we can assume that for our structure, it is acceptable to live with this small damage there. So to investigate fracture mechanics, we are testing a lot of fracture mechanics joints, as they are called. Here, I will just move it because this is a quiz that I do for my students. I'm asking if this is mode 1 or mode 2 and so on, but I will just do it correctly here. Mode 1 is the opening mode. Mode 2 is the mode where we have shear. Imagine there we have the two arms, and as we do bending, there is shear between the two arms. And then you can combine these two modes and you have the mixed mode experiment. So that where you open, but at the same time you press here to introduce also shear in the system. And then by changing this arm, this ratio here, you can change the mode mixity, as we call it. So the result of this analysis in static, when we do quasi-static loading, is to estimate the load displacement and then go to the R curve, so the curve that gives the value of G, the energy, as a function of the crack. And in fatigue loading, it is exactly the FCG curve, the curves that we have seen before. These are the curves that we developed in our case for our material. And these are the curves that you see here are for mode 1 testing, for this type of testing at different R ratios. So you see also that R ratio plays a role even in fracture mechanics. It's not only on the typical SM curve data. And we've seen also in this case that there is a model, like what we call it a total life fatigue model that we described clearly in this publication in 2012, that can describe the behavior of the material all over the experimental spectrum. And then we can use these FCG curves to derive or to estimate the crack propagation, as we said before, to estimate when and how a crack propagates, and when it reaches certain points where we think that it is critical, we have to stop the test. We have to assume that the failure is already happening. So in fatigue, by doing this type of testing, mode 1, mode 2, and mixed mode, we can also develop mixed mode failure criteria, like the one you see here for static loading, that can be also used in fatigue. But in static loading here, what we can do, we can estimate this. For me, it's a failure criterion that reminds me a lot the typical criteria that are used for composite laminates. The Chai-Vu criterion, for example, is an elliptical equation that goes from sigma 1 to sigma 2. In this case here, we have G1 and G2, but again, there is a criterion that is having this elliptical formulation. And by having this criteria, we can estimate the G propagation, so the energy propagation with crack, in certain joints that are composed by the same materials as those that we've done the tests in the fracture mechanics joints. So again, I mentioned above that we had a lot of modeling approaches by using machine learning tools, and I'll go very briefly on that, starting with this publication that we had back in 2007, where we used neural networks, and then in 2008 we used genetic algorithms to work with modeling of composites. And then in 2008 we have this common publication with Raman for applying the adaptive neurophagy inference systems, what we call ANFIs, in modeling fatigue life of composite materials. So all these methods are based on the same, if you like, theoretical background, that they need data in this input layer. Then there is the model where it is trained by using the data. So actually we read the data, we try to understand the behavior with the model, and then we have the output layer where initially we output results and we validate these results with a specific test data set. So part of the data set that is used for testing. And then when we have the model which is already defined, we can apply the model for new input data from material conditions that we haven't seen, we haven't used for the modeling. And this is how this model sometimes can be assumed to be a predictive model. So cases that we've done, we used for the implementation, we used a lot of data from different databases, like the Department of Energy database that I presented already before, a short report. There is an Optidat database for material for composite material for wind turbine rotor blades. It was a big European project. There was also a database from Virginia Tech, and there was the database that we established at the University of Patras during my PhD years ago. So for these materials, as we said, we use data for training, and we've seen that a kind of percentage of 40–50% of the available data set is enough for giving a good sample for training of the models. We've seen that we could achieve correlation coefficients of more than 90% when we train the data with these percentages. And then using these values, we could estimate SN curves for materials without using actually the entire experimental the amount of the experimental data. So the idea behind this was that we could actually simulate the fatigue behavior by using less experimental data, which means having less experimental efforts. If you, I don't know if the person that asked yesterday about this 6 specimens testing is still around, but this is related to exactly to this. The idea here is to reduce the data for that we need to do in the lab and model the behavior and then extrapolate and create more data that we can assume that are valid data for testing. But again, this validity is based, the validity of this assumption is based on the type of data that we have. And it's based on the variance of this data set. If we have a data set which is very, very broad, then probably we cannot do a good prediction of this behavior with the tools that we're using. So here I will go through some applications. The first work that we did was based on neural networks. We had a data set, then we used as input these parameters, and the output was the number of cycles. So the parameters of the test, and the output was the number of cycles. So, and I have results showing that it is very much accurate to do this modeling of the SN curves by using this neural network model. And also we can do a very nice modeling of the CLD by using exactly this model. We did also the same exercise with AMFIS. This is the publication with together with Raman. AMFIS is a bit more, say, complicated than a neural network. Actually, it creates some linguistic rules between the input parameters and fuzzifies these rules. And then by running the model, at the end, it defuzzified the rules to create or to estimate number of cycles to failure. And with this, again, you will see that we had very good accuracy, even for cases where we only used a very, very limited amount of experimental data for the training. So this means for us that you can actually reduce your efforts in the lab and have very nice extrapolations of the SN curves by using only limited databases. So we also did genetic programming. Genetic programming is a quite interesting technique in machine learning because it is based on the principle of reproduction and the survival of the fittest. So it is based on the assumption that only the best conditions or the best, if you like, combinations of parameters can survive. And the evolution operates on a lot of computer programs that are developed. So it develops. That's why it's called genetic programming, because it generates programs that can simulate the material behavior. And the representation is in trees, like what you see here. If you want to describe this equation, for example, you go from bottom to top. Here is x plus 3. So x3 and the plus is there. A multiplying 3, so 3 times A. And you have x plus 3 minus 3a, that is given by this. And then you have 2 times p. So 2 times p plus all the rest which is there. So this is the way that genetic programming describes equations in the format of trees. So like other methods, genetic programming learns from the data that we give as a training set and then produces a lot of programs, evolves programs in the programming to simulate the material behavior. And this is what we've seen in our case for different SN curves, that we could simulate the behavior quite accurately. What you see here also, this is the output. Here are points, output of the genetic programming. And this output does not follow any, if you go through this, it does not follow any specific power law curve or whatever. So there you can easily fit, or you can assume that already you have from the output an equation that can be third order, fourth order, whatever it is needed to fit exactly this experimental data. So coming back to the mention that we had before, the best SN curve is the one that fits better your experimental results. So the summary for the methods for fatigue life modeling is given in this slide. We discussed about SN curves, machine learning for SN curves, stiffness degradation, residual strength theories. We touched a bit on fracture mechanics of joints. We didn't talk about this crack density because it's related to fracture mechanics. Again, it's an idea of following the crack while it is happening. We explain a bit the complexity of each one of the methods and the usefulness of each one of the methods. And in the next slides, we'll try to go to predictive modeling, discuss actually how we use these methods to predict the behavior of the material in the long term. So what I will do today, I will introduce a couple of slides. We still have 10-15 minutes, and then I will keep the rest for the last lecture of tomorrow, if we are okay with that, with organizers. So in these predictive modeling techniques, we again can classify them in different categories. We have those methods that are experimentally based, so SN curves, CLDs can be used for prediction. We have methods that are semi-empirical or called also phenomenological, conjectural, as we see there, like failure criteria. And we have methods that are based on physical understanding, those that are micromechanics based methods or energy based methods, like those used in fracture mechanics. For me, all of them are more or less empirical, because even those methods that are based on physical understanding, they might develop the method itself based on physical understanding, but at the end, for the application of the method, you always need to fit a model to experimental data. So, and fitting this model makes the implementation to be empirical. So for the evaluation of CLDs, for example, to start with the first, I selected several data sets from the material number 1, material number 2, and material number 3 that we've seen also yesterday. And there I have the comparisons. Here I'm showing all the constant life diagram types that we've seen this morning, and how they can be applied for describing this specific material. And again, here you can, we can start discussing and seeing which diagram is best, which one is not good. We can see also the problems that I mentioned this morning with, for example, the Harris diagram is this one in C. Yes, C is Harris. And you see that depending on how we fit these 3 different parameters that we mentioned this morning, we can have good results or very bad results. And because you can fit the lines by using linear interpolation, you can fit by using power law interpolations. And there you have much differences. The same happens with this E. It's the diagram by Boestra, where we see that there is a big difference depending on the method that we used for the application of the model. So going back to the discussion here, comparison of the models is based also on the necessity of data, how much data we need to develop the model itself. Because here we talk about prediction. We want to predict material behavior. But if we use the data, so in this case, for example, this is the piecewise linear diagram. I used the data for R equal 10, R equal -1, and 0.1 to develop the model. And then the data that I predict are those data are 0.5. And I can claim here that the prediction is very good. For the Harris diagram, again, I used the data at 0.1, -1, and 0.5. You can see here that in this case, the diagram does not cross the data exactly because the fitting is on the entire data range. And then I predicted again here, the R equal, here is a mistake, should be R equal 0.5, not R equal 10. So I predicted this SN curve, and we see that the prediction is not so good. The same for this diagram, the piecewise nonlinear, I used 3 SN curves to predict the fourth one. And the same for Boestra, I used the data from these 3 SN curves to predict the fourth one. The same for Kavai, where I used only one SN curve, this one that is the critical ratio, if you remember that we mentioned. And then I predicted the other 3. And we see that the prediction here is very, very poor in this for this material system. The same happens for the linear diagram. I used these 3 to predict the other, this one to predict the other 3, and the prediction is as expected for the linear diagram, not good at all. So going to the material number 2, again the same concept, using 3 SN curves for some of them to predict the other 2, 3 SN curves to predict the other 2. Here you see the Harris diagram is much more stable than before. Piecewise linear is always accurate in our cases. The piecewise nonlinear is also accurate. Also Boestra for this material seems to be stable. Even Kavai, the diagram from Kavai is more or less good, although it tends to overestimate the material behavior. The linear is again not good as we expect. And the same for the third material. Again, here I used 5 SN curves and predict 2. I used 5 and predict 2. The predictions are good for Harris and piecewise linear. Carefully with Harris and the different interpretation, how we use or we apply the diagram, here we might have problems. But again, we see that other diagrams are good, others are not good. Kavai here is very poorly accurate. Boestra is very bad in this case also. So the summary is that we should be careful when we use these methods. We have to select the correct method depending on the material that we are using. In the previous analysis that I've done, I used only one type of SN curve, and I did the analysis for 50% reliability, so the median, as we call it, SN curve. But this, of course, you can imagine, you can do it by using different SN curves instead of logarithmic. You can use Sendesky's model or Whitney's model to fit your experimental results. And of course, you can do it for different reliability levels. And actually, a CLD with different reliability levels would look like that. The solid line is for 50%, and the dashed lines are for 95%. When we have the diagrams, the good point is that what is the prediction? As we've seen before, we have a diagram. We assume that it's an accurate diagram. Then we can go to a different SN curve and predict this line. And if we want to try now to see the prediction efficiency of the diagrams, I have some results here. Again, using the material system 1. In the first case, we see that, as expected, as we said, the linear diagram is very inaccurate. It overestimates actually the material performance for all the cases. The other diagrams are more or less the same, good, except in this case, Harris diagram, when we use the linear interpolation, that is very, very low. In another material system, I think this is the 15, this is the on-axis case. Again, we can see most of the diagrams are quite good, with the piecewise linear and linear in all cases being the best ones in these comparisons. So we have another comparison, and then I also I gave here the coefficient of correlation, showing again that piecewise linear is stable, can predict more or less with a good accuracy most of the cases that are that are used. So the summary for CLDs is that the good CLD selection is essential for a good fatigue life prediction. All methods involve the problem of mixing data. Again, the same problem that we have with the SN curves. Either we use the static strength data or not. There is a problem with the accuracy when we approach R equal to 1, so the horizontal axis, because there we have an increased creep contribution to the fatigue life, and things are not clear. We are not fully fatigue. We are not in a clear fatigue region, but we are in a creep fatigue region, and we are not certain that the predictions are correct in this case. So simplicity is offered by some models. You remember we discussed about, for example, Kawai model. It needs only one SN curve, but this is in some cases, or in a lot of cases, this is against the accuracy of the models. The more simple the model, the less accurate it is, or saying in a different words, the simple models are good for specific cases. Kawai developed his models for unidirectional carbon, and in this case it works. But then if we take this model and we try to apply this one for example, plus minus 45 glass, then we might see that it does not work well. So then I will just introduce this. I don't know what is the time yet. Yes, we are approaching the end. So I will introduce the failure criteria, and tomorrow we can go in details to discuss about them. So as you remember, we discussed in the first day, based on this publication that I had in 2002, and we said that for composites, assuming or neglecting all the three stress components in a plane stress condition, and using only the maximum normal stress does not lead to good results. So there we know that multi-axial stress states in composites are very significant. And this means that we have to use macroscopic theories that are based on the interaction of the various stress tensors, and not on the maximum stress or the maximum shear. These are the maximum stress, maximum shear are good models for isotropic materials, but are not good for composites. For composite materials, we usually need. For composite materials, we usually need to assume a multi-axial failure criteria, taking into account all the three components of the applied stresses, and assume this in the calculations. And this is mainly due to the anisotropy of the material, that especially when we have highly anisotropic materials, imagine a carbon unidirectional fabric that has very strong properties in the direction of the fibers, but then the properties transversely to the fibers are very, very low, which means that even with a very, very low stress at this direction, you might have failure of the material itself. So maximum stress criteria like this that can be attributed to the plane in this rectangular format are not good for composites. And we know that for composites, we need to use quadratic interaction failure criteria. And how do we know? So this is the explanation of the maximum stress criterion, and this is the explanation of the quadratic failure criterion. How do we know that we need to use quadratic failure criteria? We know because we have experimental evidence. We've done a lot of testing in biaxial testing, multi-axial testing, and we've seen that the best configuration for simulating this behavior is by using criteria that resemble ellipses. These criteria, as we said, they are conjectural. They are not based on any physical background. They're only mathematical expressions that are fitting the experimental results. They do not give any idea, any information about the failure mode. However, they can give an idea about this. If we see the equations, and then we see that there are in the equations, we'll see later on today or tomorrow probably, in the equations we have terms that are related to the normal stress, there are terms that are related to the shear stress. And at the end, we sum up these two to compare to failure. So in this very qualitatively now I explain. Imagine that one of these is much higher than the other one. It means that the failure mode is related to the term that is giving the higher value. And there we can say that if, for example, the shear term of this equation is much higher, we can assume that the material fails under shear. If the normal component is much higher, then we can assume that the material fails under normal stresses. So I will stop with this slide, which is a kind of visualization of how we use a failure criterion. And actually, we apply the failure criterion when we have well-defined our stress field. And the failure criterion, we should not forget, it is applied at the level of the material that we would like to apply it. What do I mean? We can have a failure criterion that represents the entire structure, but then we need data for the entire structure. We need to test the whole structure and see when it fails, and this is a failure criterion that is applied to the structure. If we want to go deeper, and this is usually what we do, we apply the failure criteria at a certain level of the material, so either at a laminate or at a lamina, because there we can analyze the stresses that happen, and there it's easier also to get experimental results. It's not easy to get complete experimental data sets for a complete structure, because then we need to build a lot of structures and test them in the lab and break them and get the values that we need. But we can do a lot of testing at the lamina level, make specimens at the lamina level, identify the material performance at the lamina level, and build our failure criterion at the lamina level. So this is what is shown here. When we have a structure, in this case it's a Winterbein rotor blade, we can analyze the stresses at a certain level. So there we have a laminate, composite laminate, where we can analyze the stresses. Then we can use the classical lamination theory, this CLT, to go to the ply level, where again we can get the stress field at the ply level. And in this ply level, we apply the failure criterion to give an assessment of the life, to say if the material, so the ply, the specific ply, will fail or not. If it fails, and this is now the description of the virtual testing that we mentioned before to do design optimization. If we assume that it fails based on the failure criterion, then we have to go back, change the configuration of the material in the blade, do again the analysis of the stresses, do again the CLT, come back to the failure criterion, investigate if it fails or not, and go all around until we achieve acceptable conditions for the material. So this we'll see more or less tomorrow. We can continue discussing about this and see how and which failure criteria we use in composites and fatigue, and how we apply them to estimate their fatigue life. And I think I can stop here. We already 8 minutes later than the planned timeline. I can stop here, and if you have any questions, you can